it is my pleasure to present Professor Leo Porter, our very own Professor Leo Porter from the Computer Science Engineering Department here at UC San Diego. And so Leo is an assistant teaching professor here, and he has a variety of research interests, many of which we'll have him talk about. He's also, he's co-taught actually several popular massive open online courses, or MOOCs. So one on the Coursera platform, it's actually a specialization called Object-Oriented Java Programming, Data Structures and Beyond, with over 250,000 enrolled learners. And also the first course in this new edX series that's a master's certificate program in data science, which is called Python for Data Science, with over 60,000 enrolled learners so far. And Leo is really interesting. I'm going to go off script. Don't be scared. So Leo's really interesting. So he was one of our own PhD students in computer science engineering. Yeah. What year did you graduate?
2011.
2011.
Yeah.
So Leo was a PhD student here, graduated, and then he was a professor in upstate New York, very similar to myself and Jim, for a few years. And we very wisely hired him back as a tenure track assistant teaching professor. And so the UC system is really unique in that we have a tenure track system, both for professors who tend to focus more on research and also for professors who focus a bit more on teaching. So it's a really unique position because not only do we hire people who are excellent as teachers, as many of you who have taken Leo's classes can attest to, we also hire people who are excellent researchers in educational topics. And actually, I first knew about Leo before he came here, actually, because Leo is actually, for being actually quite young and early in his career, he's actually one of the leading figures in the research world of computing education. And so I'm actually really familiar with some of the earlier papers he did several years ago. He's won several best papers. I think he won like all the best papers awards at the top computing education conference. And today he's going to talk to you about some of that research that led to these best paper awards. So take it away.
Awesome. Thank you so much, Philip. That was a really kind introduction. Thank you. So I'm excited to be here. When Philip talked to me about it, he described the background of all of you, that many of you are Cog Sci students, many of you are involved in HCI, and many of you have some interest in education. And what I wanted to do today was talk about peer instruction, which is my main area of research. And I had these ideas for what I wanted to do with this talk, to be honest. And I wanted to cover all these different topics. I'm going to show you what these topics are, but I'm not going to cover all of them because I realized that was just downright impossible. So what really happened is back in 2008, Beth Simon here at UC San Diego started using peer instruction in her courses. And she was kind of the first adopter of peer instruction in computer science. And since then, it has now gone from one instructor at one school to now being essentially a best practice, where a number of different institutions actually have many instructors teaching this way. Computer science here at UCSD is one of them. I'm going to talk a bit about, that's actually the main focus today, is talking about the research on peer instruction. But what's great is that this led to more research. And for those of you who are the students who are interested in getting into research, I think there's always this kind of misunderstanding of what research is, that you're going to sit yourself in a room and just think really hard, and that's going to come up with the great new ideas or new problems to solve. And generally, that's not at all the case, at least not for me. I've been tackling problems, and in the process of tackling one problem, I come across a really cool other problem. And then that leads to the next step of research. So research begets research. This research project actually led to 3 other projects. The first was realizing that publishing research to show that peer instruction is effective in classrooms does not mean faculty all of a sudden start using it. I was completely floored. I thought the second you publish those results, faculty immediately change their ways and we're done. And that's not at all how it works. So we've actually done a whole bunch of work in terms of trying to get more faculty to adopt peer instruction. This is actually the new computer science teaching faculty workshop. It's an NSF-funded project where we essentially take new computer science faculty who are going to R1 institutions, and we train them on how to teach. And we teach them a whole bunch of different things, how to design syllabi, things like that. But in the process, also teach them how to use peer instruction. The second project was a realization that we lacked instruments to measure student learning in computer science. So if you look at the other disciplines, for example, physics, they have a number of instruments that are validated that allow you to actually measure how much your students learned in a course. Those are essentially absent in computer science. In the last couple of years, we've actually had 2 show up. We had one for digital logic that Jeff Herman developed at UIUC, and we had Mark Gwisdile publish one this last fall for the very first programming course. But those are the only instruments we have right now to measure student learning. I took on an NSF grant to develop one for data structures, which is the second course in computer science. And we're about year 2 into that grant. But the reason for this, right, was that I wanted to measure how much my students are learning in peer instruction classes versus lecture classes, and I couldn't do that because I didn't have an instrument to do that. And the third direction we looked at was saying, well, once you start using peer instruction, you kind of naturally collect data, just automatically about your students through the course of teaching. And that data is actually incredibly rich. So what could we do with that data? And my goal today, again, perhaps I was a bit ambitious, is to actually talk about both of these topics. And I'm going to go fairly broad. If at any point you want me to dive into details on one of the studies I'm going to show results for, please just ask questions. I'll stop. We'll dive into the details of it. I'd be happy to. Okay? So first, I have to tell you what peer instruction is in case you haven't seen it yet at UCSD. Peer instruction is a form of active learning. So this is the classic model of a flipped classroom, right? Students do some kind of preparation before class. That might be reading a textbook or watching an online lecture. Then they take some quiz to make sure that they actually understood some of that content. But that's essentially their first exposure to the material. And that allows you then in lecture to tackle the hard stuff, the common misconceptions students have, the barriers that we know for students really in terms of learning this content, and that's what you do in class. And then after class, obviously you do homework and you take exams. I do want to say, as a quick caveat, there's lots of different ways to do this in lecture. There's lots of different active learning approaches, think, pair, share, problem-based learning, process-oriented guided inquiry learning, which is also just called POGLE. It's really common in chemistry, and then peer instruction. These are the more popular different active learning approaches out there. I do want to say why peer instruction. So peer instruction is really nice because unlike some of these other techniques, you can do it in a standard lecture classroom. So a number of these different ones require you to have a whole different space for learning, which is great, and some universities are in fact building new spaces that allow for better collaboration with their students, and that's fantastic, but I want people to adopt it right now, and they can do that within lectures, and peer instruction allows you to do that within a lecture classroom. So what peer instruction does is it revolves around a number of questions in class. So Eric Mazuro came up with this, called it them concept tests. But essentially you follow this algorithm 4 to 6 times per class. And the algorithm looks like this. You pose a question to your students. This is a question from CSE 105. They vote in on it. You as an instructor know what they voted, right? You then open it up for discussion, so your students talk with one another about it. There's lots of reasons why you might want to have your students discuss this. I mean, this was actually the thing that took me the longest to realize you needed to have. So you need students, those of you in Cog Sci know this much better than actually I do, why it's so important for you to be able to express your ideas verbally in terms of then learning it. You also want your colleagues to challenge your understanding so that you can then respond to that and think differently about it. But the biggest factor, I think, is actually the novice expert literature tells us that experts and novices speak different languages. And I didn't really totally understand that until I heard 2 students talking back when I was teaching a CS1 class. And 2 students were talking, and they were just talking with their friend. They're like, hey, you know that thing with the method? It has the same name but different arguments? And the other guy goes, yeah. And they keep talking. And I go, that's method overloading. I realize they don't know the term, right? And then, of course, I'm also correcting them that it should be parameters, not arguments. But that's the language that they speak, and it made sense to them to speak in that language. If they talked to me, I would have used the word method overloading, and I would have lost them, right? So it's important for novices to speak with other novices in the process of learning. After the group discussion, they vote again, which is great for me as an instructor because now I've got a snapshot of where they stand. How much of my class understands this, how much of my class doesn't. And if it's 80% of my class who understand it, I'm going to spend just a little bit of time on it. And I'll move on because most of the students already have this down. But if 30% of them have it right after the group discussion, I've got a serious problem. And I'll essentially change my lecture dynamically in order to address this common misconception and try to figure out why the students aren't getting that, rather than just running ahead with half my class not knowing what's going on. Right. So this is the algorithm. You follow this again 4 to 6 times per class, and then that's interspersed with some small lecture content. Does anyone have questions about what peer instruction looks like then? Actually, I'm just kind of curious, how many of you have seen this in a class? Oh, awesome. Okay, so that makes me so happy.
I have a quick question.
Yeah.
Sorry to put this off to later if you
Yeah.
want. I mean, one thing about any of these newfangled approaches is that the student reception can be mixed. And at some point today, I was curious if you could talk about that.
I'll definitely talk about student reception of it. Yeah, yeah, absolutely. In fact, I think that's the next slide's coming up. So thank you, Scott. So what I want to do is give kind of an overview of what we know about peer instruction in computer science, and actually address Scott's question first thing, which is, well, how do students view this? Do the students like this? Kind of absolutely. So we've had a number of studies. I actually won't dive into the details of this, sorry, Scott, because we've actually had so many different papers now kind of showing students value peer instruction in their classes. And by valuing it, what I mean is that when you give them this statement, 90+% will agree with this. They want more instructors to teach like this in their classrooms. And this is true at liberal arts institutions, this is true at R1s, it's true at primary undergraduate institutions, it's true for lower division classes in CS, upper division classes in CS, it's true for the person who developed the materials, it's true for the person who adopted the materials. So we've shown this in all different kind of contexts, and we just keep consistently getting back that 90%. That doesn't mean everybody, and there are some discontents.
So, but you think, my sense, I totally believe in this approach. I think it's awesome. I use a limited version of it. My gut estimate would be that the actual student support is not quite that strong, even if it should be.
So we have pretty good survey participation in terms of the ones who agree that they want to see this. I'm not sure.
Guess, what I wonder is, I mean, that survey question is a little risky in that it's called our approach. And if you recommend anything, people say yeah. And so I would be curious, like, I think if you ask the question, clickers are disrespectful to the complexity of my brilliance or something like that, people would also say
we did have some counter questions on this survey. I wish I brought the results for this. There were some counter questions where things like knowing the right answer is the only part of a clicker question, and something like 20% of students will agree with that, which is what you want to see, only about 20% agreeing. We have some student CAPE data that I'll actually show a little bit later, which might actually be a more kind of natural finding of this. So if it's still unanswered after that, I'd be happy to talk more about it. Yeah. So I was actually going to say that this has essentially been shown in so many different contexts at this point, at least for this survey, that we're actually going to focus on some other outcomes of students. But I'll come back to the question of CAPEs. Okay. So the first question we kind of asked was, do students learn more? And I already told you we lack assessment of student learning in CS. So we had to use proxies. The proxies are final exams. Final exams have their problems. We can spend a whole bunch of time talking about why final exams aren't perfect measures, but that was essentially what was used. So this is actually a study by Beth FS Simon here at UCSD, where this was in CSE 3. She had 2 sections of the same class. She was the professor for both sections. She taught one with lecture, one with peer instruction. She made a conscious effort to make sure all the peer instruction questions got given to the students as study materials, so at least the same content got given to both sections. And then she gave identical final exams. And these are the results. So what you have here this is a histogram of student results. What you have here are the results for the lecture class, so the standard instruction. And in dark blue, you have the peer instruction class. So first off, statistically significant difference. It's a 6% difference in terms of final exam performance between the 2 sections. But what always stood out to me with this result was, what in the world is going on down here, right? So at the standard instruction class, you had a pretty decent number of students show up for the final exam and just vomit, right? In the peer instruction class, there was 1, right? So there's 2 possible explanations for this. One, if we're being really critical, is to say, well, if I'm designing a final exam as an instructor, and I have all this feedback from my students from peer instruction, I have a better way of gauging how well they're doing, and I should write a better final exam. But that's actually not a problem here, because it's the same final exam for both groups. The other hypothesis for what's going on here is just, if you give students feedback every single class about how well they're doing, they might catch on that they're struggling earlier, right? So this is a really nice finding. It's actually been replicated. I won't show the results from the replication study, but it was done at the University of Toronto. Dan Zingaro, he changed this experimental setup to be him against the most popular lecture instructor, to say, well, maybe Beth didn't put her whole heart into doing the standard lecture. I'm going to do wholehearted lecture instructor versus me, and it had the exact same findings. So it was about 5% difference. I think it was not statistically significant because I think the p-value is like 0.06. That's just really a sample size issue, not an effect size issue. So good news, yes, our students learn more in lecture. The next question we had was, do students learn during this process? Is the process successful at teaching students? And the way that we went about this, and let me just be clear about the question I'm asking. So a lot of papers prior to our early work on this, actually some of our colleagues' early work on this, was to say, well, student learning is the difference between this vote and this vote. And if you're going to be critical about that, you're going to say, well, wait, they could have just copied some perceived smart student in the group, right? They didn't necessarily learn from that. They just know who to mimic the answer for. So what you'd want to do then is essentially ask another question after this and say, find out whether or not they learned. And who did this was actually Michelle Smith, working with Carl Wyman and a number of others, added this extra question in biology after the group vote, which is isomorphic, same topic, same concept, just different question to see if students actually learned from it. They actually published their findings in Science on this. And it turns out that yes, in biology, students do learn from the peer instruction process. We did a replication study. So in our replication study, here are the results from it. So these are % correct. So in blue, you've got the individual vote. In red, the group vote. In green, you've got this isomorphic question. And what we're looking for is to see if they didn't learn anything, we'd expect them to be essentially the same as the blue bar. It's not. If they learned perfectly from their neighbors, we'd expect it to be on par with the red bar. It's not. But most of what they learned was actually retained. And this was true both in a computer architecture class and in a computer theory class. Our results actually mimicked the results from biology quite closely in terms of the percentage of students who retained what they learned from the discussion. Now, we were very happy about this result, but we were a little miffed about the setup of the experiment because this is just measuring student discussion, and I like to think we as instructors have some impact. I like to think that. So what we did was we changed the experimental setup to now do classroom discussion. So sometimes we had individual vote, then the instructor-led discussion, and sometimes we had the instructor-led discussion and then the individual vote. And I do want to point out that we had to have some controls on the instructors. The instructor who taught this felt fairly limited. Because as an instructor, what I like to do is say, okay, so if I change this question and you ask this differently, this is how it's going to be. And if I change it this way, this is going to be the new answer. And the instructor couldn't do that because they knew there was another question coming and they didn't want to answer the question that was coming next. So this is perhaps pessimistic on what the results are relative to natural occurrence. So what we had was, so this is just using peer discussion. So here's the individual vote. This is the second isomorphic question. I got rid of the group vote because again, we know that's a bit noisy. So this is just how much did they learn from the peer instruction process, and this is how much they learned from just the peer discussion, and this is how much they learned from combined. And really we're just looking for that difference, right? So you got about 15% improvement from just discussing with your peers, you get about 23% on top from the instructor intervention as well. So the instructor is valuable, we are adding something. That's good news for our jobs. So we like this finding. I do want to give a quick aside here, which is that this is actually the case for giving hard questions. So if you use peer instruction in your class, I've got a good argument for why your question should be difficult. So on the left here, I've got easy questions. So this is not scaled by the number of students. There are more students in this bin who answer correctly this question, right? This is an easy question, so more than half the students got it right, and we're essentially measuring how far they get. On this side, we've got the students who got it wrong. There aren't many of them for an easy question, and what you find is after instructor intervention, about 77% of them have corrected their misunderstanding. What's neat, right, is for hard questions, I've got a much larger population of students here who got it wrong. And you know what? By the time we're done with peer discussion and instructor intervention, we're almost at the exact same place. Now, granted, you may spend more time on the hard question than you do on the easy question, but you can actually you get much more learning out of the hard questions than you do the easy questions. Admittedly, that's somewhat obvious. If you have more students who get it wrong, you have more of an opportunity to improve. So, good news is this essentially has been replicated. I should mention actually that Michelle Smith also did this instructor intervention study as well in biology, replicated essentially the same findings that we had. So at this point it's been replicated both in biology and computer science, and we've replicated our own findings. This is pretty well established that students learn from this process at this point. The next thing we wanted to find out is how does it impact student course outcomes? And this actually came about as a natural experiment. So this is ad hoc. This was not a design experiment. We did not have this in mind when we adopted peer instruction here at UCSD. What we did was, after it had been running for about 5 years, we just looked back at the last 10 years of courses at UCSD, specifically these 4 courses that had instructors teaching both with standard lecture and peer instruction. And we just asked the natural question, did it change fail rates at all? And by fail rates, I mean, I'll get to the fail rates here in just a second, but I just want to say that this data set is huge, right? 10 years of courses here at UCSD in the CSC department, lots of students, right? So we've got about 8,600 students in the standard instruction classes, a little bit over 2,000 in the peer instruction classes. This isn't just one instructor, this is actually 7 different instructors using peer instruction, and we've got 16 instructors doing the regular classic instruction. So big data set here. We define fail rate to be what the literature says, which is DWF, so getting a D in the class, an F in the class, or you withdraw from the class. There are drops. I'll talk about those a little bit later, but we're going to focus on the fail rate for now. What we found was actually pretty remarkable to us. So these are the 4 classes that we studied. We saw a statistically significant effect in a drop in failure rates for all except for CS 1.5. I'll talk about that in just a second. And on average, we saw a reduction from 20% to 7% in fail rates. And in terms of, this is good for students, right? You want fewer students failing the classes, but it's also good for the institution, right? Because a failed student is a student who retakes the class. That hurts our throughput in terms of the number of students who can get through our courses. So overall, this is a large reduction in this. I do want to just quickly give you my theory for CS 1.5. I don't have any data to support this. Our best guess on why we didn't see a reduction here is that this follows CS1. You know what? If you fail this class and you retake it, you just don't go on. The people who would have failed here just don't show up. They don't bother. Now, what you could say pretty accurately as a criticism is to say, well, wait a second. What if just the good instructors were the ones to adopt peer instruction? Maybe this is just a measure of like good instructors versus bad instructors, right? Well, it turns out, thankfully, we have an answer from this from the data because we had 4 instructors who'd switched. So we had data on all 4 of them. And it turns out they look almost exactly the same as the general population. So when they switched, they saw their failure rates drop as well. So this seems to be the pedagogy, not the instructor effect at this point.
I don't know, you might argue that the good instructors are more willing to switch or adopt new techniques.
Yeah, you still could, yeah. But again, it was a good instructor who switched. So the question is, why is that good instructor having 24% of the class failing before? That's somewhat problematic. Yeah, good point though. And that's how you're going to confound our CAPE data later. Keep that in mind. Yeah.
Just slightly off topic, that's a hideous fail rate. Isn't it? 0.25%? Excuse me, of the whole population?
It is, so for the intro courses, so for CS1 and CS 1.5, that actually is pretty comparable with national averages. In fact, we might actually be a little bit nicer than national averages. So something like 1/3 of students fail their intro programming course. And that's a bit dated, that's data from about 3-4 years ago before the huge enrollment surge. For our upper division classes, yeah, this is actually really problematic, right? Why do I have an upper division class that's failing 24% of our students? Yeah. I don't know how to critique, but it's a good point. So the good news is, let me show you really quick a quick dive into CS1, because this is actually what was most striking to me when I started looking at the data. This will actually dive to the point that you were making. So this is our 8A class. This is CSE 8A. I've somewhat anonymized these, but what we have here on the left are the failure rates. So fail is blue, red is withdraw, and we have these are the standard instruction classes and these are the pure instruction classes. And it's so telling, this data, right? The average standard instruction class is worse than the worst pure instruction class. The average pure instruction class is on par with the very best standard instruction class. And when we saw this, we had to start being skeptical. We said, well, wait a second, what if pure instruction causes more students to drop early? Right? Like maybe they're getting data early on that says, I'm not well equipped for this, maybe I should drop earlier in the course. Turns out we were wrong. Drop rates are actually lower for pure instruction than they are for standard instruction. And then so that's actually the main key finding, but it also told us we may have some problems with our program, right? Because we have courses where over 70% of our students either dropped, withdrew, or failed. That's a real problem. Real problem. So we have some hint that this affects students' failure rates. This is one study. It was an ad hoc study at UCSD. Has not been replicated yet. We've got 3 institutions that have enough faculty teaching with peer instruction that we're trying to get them to do a replication study. Problem is they've got the confound of massive enrollment spikes over the same time period that they adopted peer instruction. So we're trying to figure out how to best set up that study. Our next question is, does it impact student retention? And I'm going to walk through this a little bit quicker. When Beth Simon actually led the change to 8A, and actually I was her TA back at the time, that's how I was involved in this. She adopted 3 best practices. So first was putting the computing in context, so using media computation, so it's meaningful computing for the students. You're not just printing for loops, you're manipulating images. She created community by using pair programming, so instead of being alone in the lab at like midnight and you get this 75 errors from your program, and you say, I'm out of here, you actually have someone with you to go, oh wait, I think you missed a semicolon, and everything's okay, right? And then she also adopted a best practice. These were best practices from computing at the point at that time, and this was a best practice from physics at the time. And again, we're now looking at post-hoc analysis last 10 years, same kind of data set that we were just looking at. Again, large data set because this is 8A. Lots of students go through it. We had, again, thousands of students essentially in both before the best practices and after the best practices. And lots of different instructors actually adopted this as well. And the way we defined retention was to say, how many people are around a year later? Now, you could say, well, how many of them end up majoring? But there's so many confounds throughout the program if you wait that long, if you wait 4 years. At the same time, we could have said, hey, do they stick around for the next class? But that's also problematic because maybe they just fail the next class. So what we want to do is try to find something in between. So we picked 1 year retention. It was also, we published this in 2013, and that was actually the data set we had. So we didn't actually have data on whether or not they graduated yet, to be honest. I guess we had 1 cohort who had graduated at that point. But we looked at these numbers, and what we just tried to see was, were they different? And so here's, again, I'm cutting to the chase with all the results here. These were the retention before our best practices and after the best practices. So this, again, is, perhaps to your point, a real criticism of what we were doing before, right? Because 50% of the people who walked in, enrolled in 8A and said, I'm going to major in CS, half of them are gone a year later. That's a real problem. After the change, we're up to 81% of them around a year later. So really excited about this result. I'm still of the mind of attract and retain for computer science. I know we have lots of students, but I still think that way, and I think we should keep thinking that way. This is a maybe, right? Because did peer instruction cause this? We don't know, right? We had media computation and we had pair programming as confounding effects with peer instruction. It might have improved this, we don't know. Does it scale? And the reason that we asked this question was these booming enrollments, right? If you look at essentially any university, their enrollment in CS is just skyrocketing. This is true of computer science here. Led to us kind of capping our major. And the question just was, as our class sizes get bigger, do different pedagogies scale better to larger classrooms? And this is our first look at this. We actually just published this last year. This was actually my grad student who led the work on this. What we did was we grabbed all the CAPE data for classes here at UCSD within the last, I think it was, from 2012 to 2016, and we just tagged them as essentially peer instruction or non-peer instruction. And these are all the CAPE data, so all the students in the room who fill out CAPEs, you recognize these questions, right? Did the instructor explain the content well, right? And we as faculty have looked at this probably more than we should admit. And the two that we as faculty tend to care the most about, right, are do you recommend us as instructors, and do you recommend the course? And kind of first off, when you look at these data, you realize it's a really big scatter plot. There's a lot of stuff going on here. It seems like the green is above the yellow, but we kind of already knew that students liked peer instruction. We know it's actually not true for things like, is the course more difficult? That doesn't seem to be much going on there. They seem to overlap pretty closely, but in terms of do you recommend the course or do you recommend the instructor, it looks like there's a real value to peer instruction. In fact, if you kind of look at all the different courses which were in our data set, we had so many students, by the way, that all these passed statistical tests because of just sample sizes, not necessarily effect sizes. But we had essentially peer instruction is preferred by students, both in terms of getting better instructor ratings and in terms of getting better course ratings, for all except for one course where there was a slight advantage for standard lecture liking the course more than not for discrete math. But this is a known finding, so I actually won't spend a whole bunch of time on this. I will go on to say what our original plan was to look at scalability. And if anyone is an expert in terms of statistics and looking at this data, we are actually looking for collaborators. Because what we did was we created our own metric to essentially try to figure out scalability. We essentially graphed that data you just saw, but we graphed that data controlling for a bunch of different things. We made sure that we weren't looking at slopes between, say, an intro class against an architecture class, right? We only looked at slopes between the same classes. We said the slope mattered more if you had a really good data set. You had lots of classes that are small, lots of classes that are big. Anyway, we did a whole bunch to scale this. I'll cut to the chase and just say this is essentially what came out. And it's an indication, an early indication, we think, that peer instruction is essentially scaling better. Right? As class sizes get bigger, the ratings aren't falling as much in terms of how much the students value the class as they did for lecture. This is an open area. We just got started with this. Does it actually help answer your earlier question, Scott?
For the most part, yeah.
Okay.
Yeah, this is amazing. I am a little surprised to see the drop off, the gold bar in the non-peer instruction, because in cognitive science here and in computer science at Stanford, I don't think you see that same class size drop off.
Interesting. I'd be curious to look at the Stanford data.
Class size and enthusiasm are less correlated than I would have thought. And I mean, some of that might be that better instructors gravitate to larger classes, so they kind of balances each other out. But we can talk more offline.
Oh, that's a really good point, and that actually a confound to the study, right? Is that perhaps maybe just the better instructors are the green dots here who have adopted peer instruction, and that we actually couldn't control for well here. So thanks for bringing that up. So at this point, we essentially have some indication that it scales better for large classrooms, but more analysis needs to be done. It's an open question. So that kind of actually wraps us up for findings on the efficacy of peer instruction. I kind of want to move beyond just looking at the efficacy. But if you have questions, this might be a good spot to actually take them. If you have any questions so far.
I have one quick one, which is, which attribute of peer instruction do you know, it's a constellation of practices. Is there one that you think is the most important?
You know, that's a great question. Which element is most important of PI? I don't think we have a good answer for that. I mean, I think it's important to have the group discussion. I think it's important for the instructor to have data about how well their students are performing. I think it's important to challenge students in the classroom. I think it's important to take breaks from just lecturing at them, right? I think all these things are important. But we kind of like to think of it as almost, when we talk about faculty adoption, we say you should adopt all of this, right? Because I don't know if it's the 10 days or the dosage of the antibiotic that makes it work, but don't stop at 5 days and don't take half the dose, right? So we're not sure of the pieces. Thanks, though. Yeah.
Have instructors who adopted peer instruction changed their syllabus accordingly, or was the course content the same?
So the course content generally tends to be the same in terms of people who adopt peer instruction. The syllabus has to change usually because you encourage students to participate with clickers. That's usually the only substantial change. You do also tend to talk a little bit more about what's expected of the students in the classroom, that they engage and they're part of the discussion. But mostly the content stays the same. Yeah.
What was the training for the instructors and the faculty adoption of how do you create good clickable questions? I imagine you could create some crappy clickable questions.
You do. In fact, almost every one of us who developed questions, we create crappy ones when we started. So what you do is you create some definitional question that's really easy when you first start, and those are terrible. Those are just flat out bad questions. And what you do is you go, well, what's that really crazy hard question I asked in my midterm 2 years ago? That's your best clicker question. So you find really good hard questions that have students discussing, arguing. I have questions that Intel didn't know the answer to and spent billions of dollars going multiple directions and then found out the answer. But I asked my students, what would you do? And it leads to really good discussions. So hard questions that are open-ended that allow the students to discuss and argue are fantastic. In terms of the training for the faculty, it really varied. Faculty adoption, again, is this really difficult problem. We actually have on our grant for the faculty adoption, Charles Henderson, who evaluated the physics workshop, which was kind of one of the first attempts to really get large-scale faculty adoption of best practices. Anyway, it's a really hard problem. We've trained them in different ways. So if they go to the faculty workshop, they get a whole bunch of kind of observe it and also try it yourself kind of practice. But a lot of what actually makes adoption work is personal connections. So it's someone coming to me and saying, hey, I'd like to teach CSE 100, I'd like to use your materials. And I go, okay, here are my materials. By the way, they're peer instruction materials. Let me talk through how you teach that way. And that's what leads to the adoption, more so than the workshops, unfortunately. Yeah?
Are you able to look at whether diversity or stability of peers within a course matters? Like, do you want to pair folks up with the same person, or do you want to rotate?
So I think Christine actually has a paper on this. I'd have to pull the data on it. It was a SIGC 14 paper where she did a whole bunch of different pairings in terms of homogeneous, heterogeneous, and there's just no findings from the work. I think that's actually still something to be explored, but at this point we don't have a good answer on how best to group your students.
And it's all pairwise?
It was usually 3s or 4s. Yeah, groups of 3 or 4. Okay, yeah, go ahead.
If the professors are trained before they swap to peer instruction, briefly, like you talk it over, but you're talking over teaching practices with them. The hope would be that if you're talking over any teaching practices with them, even just lecturing, they would improve. Is it possible that like these results are confounded by everyone who swaps has just got some like focus on teaching, and so it doesn't really matter what that focus, what part of teaching they're focused on, but some focus in that vicinity and they can improve.
So I think a lot of faculty talk about teaching. I like to think that they talk about teaching beyond the adoption of other practices. I would say that not all of the people who adopted this went through this really close discussions about how to teach it. They did adopt materials, and maybe the materials were better. And I think there might be some signal there for sure. But it's hard to control for that. Yeah. Oh yeah, go ahead.
So all of this data was from computer science courses?
Yes.
And I'm curious, do you have any data or have the opportunity to compare and see how this, looks like in other subjects or departments or?
So physics has looked at peer instruction a great deal, and they have validated instruments to measure student learning. They've had 6,000 person studies to show that the learning gains on the forced concept inventory is about a factor of 3 using peer instruction than standard instruction. So it's actually a pretty definitive story within physics. Biology has done a number of these studies. They were actually the ones who wrote that science paper on isomorphic results. They don't have as many, I don't know of as many failure rate papers from those disciplines, but in terms of student learning, that's actually been looked at in biology and physics. Chemistry has been mainly POGIL for a long time, and I'm not sure why. POGIL got early inroads, I think, in chemistry, and most of what goes on in chemistry is POGIL for active learning. All right, so what I'll do is real quickly then, I don't want to run late, I just want to real quickly introduce the predicting of student outcomes, because I think it's actually the next step, is to stop saying, let's keep trying to show this pedagogy is effective, is to say, once you're using this pedagogy, what now becomes possible? And it turns out you're collecting data all the time for your students, and we asked just, is this meaningful for student outcomes? And I'm going to go through this somewhat quickly. What we initially asked was just, does attendance matter? Maybe clickers just get you into the classroom, and by getting you into the classroom, that's what kind of predicts your outcome. If this looks like a complete chaos on a scatter plot, it is. By the way, I've only got the bottom quartile based on performance on the final exam question, top quartile just to help visualize this a little bit better. Turns out attendance actually isn't very meaningful, right? You've got a whole bunch of people who come to class all the time, but they actually kind of bomb the final exam question. You've got a whole bunch of people who basically never come to class and yet do really well. So this doesn't make much sense. So what we did next was to say, well, wait a second, what about how often just total number of correct clicks? This helped. So now we've got a better slope here. What's missing, right, are the people who click correctly all the time and do poorly on the exam. They're just not there, right? They're not in this data anymore. But you do still have these people who never come to class and yet somehow they do really well. So what we did then was just to say, as a percentage of the things you answer, how well these things correlate, and it turns out it actually correlates pretty well. And we have very few people kind of in this group who usually answer correctly but do poorly, and fairly few people who answer wrong most of the time and yet still do really well in the exam. So this gave us a signal that perhaps these peer instruction questions are meaningful and the correctness on these questions is meaningful. So we looked at correlations, and this table's a little big, I'll jump to the chase here. It turned out for a CS1 course, the correlation with the final exam and the correctness in weeks 1, 2, and 3 was actually incredibly high. We were pretty surprised about this. Again, this is week 1 through 3. This isn't the days before the final. This is early in the term. And in fact, the stuff right before the final actually isn't as well correlated. So it took us a little while to figure out what was going on here, but it's actually about topics. So what do you learn in weeks 1, 2, and 3 of an intro course? You learn variables, conditionals, looping. What do you test on a final exam? Basically every question on a final exam involves variables, conditionals, looping. Right? It's hard to find a final exam question that doesn't do that. What do you learn in week 11? You learn how to sort, right? How many questions are on the final exam about sorting? 1, right? So what's actually on the final exam in terms of coverage is much heavier, the stuff you learn very early on. So that somewhat explains why we saw this massive correlation. I do have time to say this really quickly. We did also look at which questions are most predictive, because I think this is actually an open area that we're going to head to next, which is to say, if I know what's predicting student outcomes, if I know the questions that are meaningful, maybe this could help me focus in on these concepts or spend more time on them. And the way that we looked at this was based on Bayesian decision theory, where there are some questions that are really hard. If you get it right, you're a good performer. If you get it wrong, I don't know anything about you. We have questions that are within the realm of necessity, which means it's an easy question. If you get it right, I don't know anything about you. If you get it wrong, you're in some serious trouble. And then we have questions that are, in terms of accuracy, basically if you get it right, you're in good shape. If you get it wrong, you're in bad shape. We are focused on essentially how well do you do on a pretty common question in CS Ed that focuses on conditionals and loops. I won't dive into the details of that. We're short on time. But what I want to show you is essentially, for those of you who've ever taught coding, this might be interesting to you. So what's the most sufficient? What's the one that's really hard, and if you get it right, you're going to nail the test? It's actually this question. It was the top one from the course. In the weeds here, they're using the length of this list to decide how far to go. You walk off the end of this one. If you can catch that, you're going to do really well in the final. If you don't catch it, we actually don't know much about you. For an easy question that predicts whether or not you're in trouble, if you can't essentially take these arguments, plug them in as parameters, and figure out what the return value should be, if you can't do that, you're probably not going to do very well on the test. If you can do well on it, actually we don't know much about you, right? And then this one actually tells us both directions. If you can trace through this to say, yes, this if statement happens, oh, now x is in fact 4, so this is actually true now too, so x becomes 1. Oh, but I don't execute the else statement. If you can trace through that, we actually know a lot about you. We know you're probably going to do well on the test. If you can't do that, you're probably going to do badly on the test, right? So this allows us to now focus in on common misconceptions and think more about what these concepts are. I got time. So how can we predict student outcomes? So this is what, we just got an NSF grant on this. This is a new focus of our work. We are trying to figure out how to predict student outcomes and also help them once we figure out that they're in trouble. So what we do is essentially apply machine learning to this data, right? So I've got a whole huge data set from a previous term of all the clicker results, and I've got final exam scores, which I don't show here, but I got final exam scores for the students. That's my training data. My test data is the new term worth of data, right? So as of week 3, I feed this data into my machine learning model and out spits the people who are in trouble. It's essentially our flow. I'll skip this for time's sake, but it turns out we can actually predict with about 70% accuracy who's in trouble and who's not. So for about 21% of the class, we can say, you actually do need help, and we can predict you as needing help. For about 48%, we can say, you're good, and we don't need to help you, and we're right. But then for this remaining 30%, we're wrong in one direction or the other. We think you're okay, but you're not, or we think you're not okay and you are. What we like about this, by the way, there's lots of work on predicting and modeling student data, but what's nice about this is prior work looks at grabbing data about you before you came to school, right? We grab your SAT scores, we grab your grades in different classes, we might grab protected data on you to help model and better understand you. That's really hard for instructors to do, to get access to that data. So that's really problematic. The second problem is there's a whole bunch of modeling work which looks at the end of the term at figuring out modeling a single term. Well, that's pretty useless, right? I want to model my students' next term, not this within a single term, and this actually does both of these for us. In fact, if you just teach with peer instruction, you get this data naturally. We're working on trying to make it so that you just automatically know who's in trouble. Our next steps of this first is to say, does this work for more than just CS1? So CS1 we've been able to predict pretty well. We have a paper in preparation right now, which basically shows, no, it's not just CS1. It's actually true for multiple institutions. It's true for multiple courses within the CS major. We would like to automate this prediction process. Right now, yes, you naturally collect the data, but there's someone who has to kind of pair questions to one another. We could do this. This is solvable. So this is kind of a next step for a grad student. We might actually want to help the students, right? So there's this whole work of, I want to predict who's in trouble and then do nothing about it. Like that's not right. So, I mean, right now all I can do is essentially tell the students, I think you're in trouble of failing. That's probably not the right thing to do. So we need to think about what the right interventions are. For those of you who are like, oh, I got a really good idea for an intervention, I don't mean to depress you, but the intervention literature is essentially full of mistakes. So everything you as instructor want to try generally helps good students. So hold extra office hours, good students show up. Hold help hours on the weekend with the TA hosting it, good students show up. Offer extra credit, good students take advantage of it. So it's actually rife with error. So we're actually doing a really careful qualitative study right now to figure out why students are in trouble and then try to better understand them so that we can do something about it. And the last step, and this is an open question essentially for machine learning researchers, is we want meaning from the model. Since we started using machine learning, we're using more advanced models. And actually extracting back out what the model learned is apparently a hard question in machine learning right now. So for the more advanced models. So as that advances, I think we have a better chance of figuring out, kind of reverse engineering, well, what was that concept that was so tricky for the students, and now I can do something to help improve student understanding of that one concept. Okay, thank you all for your time. Appreciate it.